And okay, so let's continue. Let's begin the automatic control system or linear control system. So draw. So linear controls system. Okay. So whenever it's too much, will stop me. Okay. Because I know I'm such a torture for students. So okay. Why I name it linear? Because as discussed, what I'm going to discuss here on vibration. So because we are dealing with the linear differential equations, differential equation, and differential equations that we deal in the undergraduate level. So they are in the time domain. So we're going to transfer this linear differential equation to the frequency domain, omega, or S domain. I'm going to teach you in detail. That's right. So that's why we are controlling the linear system. In the MATLAB coding, I'm going to show that the linear controller sometimes works well for the nonlinear systems, I mean nonlinear differential equation. Okay, so whenever we see, as I'm going to teach you nonlinear differential equation, with some tools that I taught, I'm going to also teach here the Jacobian metrics, or the what's the name of that? Jacobian metrics and the Taylor series expansion. We're going to transfer it to the linear differential equation first. Okay, this is how we work in automatic control class. Then I'm going to transfer to frequency domain, or omega. Okay, so after linearization, after we did this, okay, and we transfer to the frequency domain, the course is focused on three objects that we have to tackle one by one. Okay, if you have unstable system, like as the pendulum, inverted pendulum, I'm gonna explain right now mathematically. You have to design a controller. To make it stable, to make unstable system stable. This is you as control engineer after graduating from SDSU. You have to be able to design a controller to make systems stable. B, modify your controller that you're designing. Modify transient response. So I'm going to define it later, but you have seen the vibration, right? In the vibration when I was teaching you, or ME432 that you had, if this is this kind of response, we name this vanishing phase as transient response, and this steady state as a steady state phase. Well, I'm going to define it here. So we're going to modify it with respect to what? With respect to, say, MP, remember? Maximum peak overshoot of the system. We want to modify it to keep it at 25%. And based on demand of your boss, whatever, or settling time, we're going to define it, okay? And your controller has to be able to remove steady state error signal that we're going to show as E of t. What does it mean? Let me tell you. With the simplest that you are experiencing every day in your home. So in your home you have AC, And these days in your AC, you want to keep it at night, say, because it's chilly. So you want to keep the room temperature, I don't know, at 75 Fahrenheit. That's right. This is what you want. And we name this in control eventually, as I'm going to teach you, as RFD, reference signal. This is what you want. This is what you want to follow in the control. But after turning on the AC, maybe you have this profile. Maybe your AC doesn't work well, and you have this gap. This gap is error of the signal. So your controller must make error signal when times goes to infinity to 0. So after designing the controller, eventually after passing this course, you're gonna have this. Here we go. This is the error signal of the system. Or even that you have a modern car, that you have cruise system. Cruise system is in a highway that you want to drive a car. Look at here. At I don't know, say this is time. This is velocity of your car, and you are here. You are I don't know, at 55 miles per hour. Currently you're driving, but you want, when you turn on your cruise system, you want to push it to 75. Here, 75. Exactly, your car implements the PID controller that you're going to learn here, and does this. There we go. So you see, everywhere is control. Robotic systems. You want to push the robot end effector to some 3D orientation and position in space. Controller. Now, these days, everything is controlled. Every dynamical system is controlled. Name it from the room temperature to the robot to the car to whatever you say. The mission on the Mars, they are controlled. Okay, when the rover on the Mars landed perfectly, meant this: the error signal is 0. Clear, everybody? Yes. So, can I go to the next page? So now I'm gonna give you the most famous, as I promised, in the vibration course, and the most important example to visualize some concept like noise, because I said your controller must error signal. Are you with me? Okay. Error signal and noise. Okay. I want to visualize noise. What's noise in the control system? And what is block diagram in the control system? By a important example, block diagram. Block diagram. And what's the reference signal? These are the concept reference signal. What is the output of the system? These are technical terms in the control. What is error signal? What is feedback? This is super important. What is feed forward? What is open loop? What is closed loop? I try to teach you by a heavy mathematical that I taught in the vibration course and take you to other level of the control. What is that fabulous example that I promised you already in my old classes? Moving pendulum. Remember, guys? And I said, if this is the hip of your body, and I can model your leg as a pendulum, and I assume the mass of your leg is long at the end, and the length of your leg is massless, and for God's sake, when you're moving, your hip has a displacement of x of t changing with time. So when you walk, the length of your leg makes angle with the vertical position, theta. Moving pendulum can be assumed as a simple, very simple model of your leg when you walk. And you cannot believe me, even this has application in the rover on the Mars. Yeah, because rover moving, and you can assume you have 1 degree of freedom robotic arm that picking up the Mars soil and putting back on the rover. Simple like that. And the art of engineer is not to model any engineering problem as a complex formula. The art of a good engineer is to simplify and break it down to a simple mechanism. Then add the details. Okay? So, being said, this is the joint O, and from high school, from trigonometry, this length is L sine theta, and this length is L cosine theta. The first mission is, as a control problem, derive equation of motion of this system, and then judge it is linear differential equation or non-linear differential equation. If linear, fine. I'm going to teach you the week after this through the Laplace transform to transfer to the frequency domain. If not, first we have to linearize and then transfer to Laplace transfer to the frequency domain. So as you taught, and I or other professor taught in dynamic course, what's the name of this equation? Come on. Also, I taught in the vibration. What's the name of this equation? Moment equation. Sum of moments around point O is I, mass moment of inertia around point O, angular acceleration. This is mass moment of inertia. Mass moment of inertia. Okay, from the dynamic course ME220, what you're gonna do, you have to plot the forces, free body diagram, mg, and if you cut the system from here, you have a reaction force from the joint, say Fx and the Fy, right? By setting up the coordinate system from dynamic course here, x, y. Then I can apply this around the point O. Yes, am I right, guys? Can I apply this around point O? Can I? Anyone? Obviously no. Because in the vibration and the dynamics and the other courses, multiple times I emphasize that the moment equation is only valid around fixed point or mass center. There we go. Okay. Point O is moving. X of t is not a fixed point. So what you're gonna do, you're gonna go back to dynamic course, and you're gonna apply Newton's second law here. Sum of the forces in x direction is m ax. Sum of the forces in y direction is m ay. We do have the forces mg, fx, fy, but we don't have accelerations, so we have to calculate. Again, going back to kinematic section of the dynamics, you get the vector of mass center with respect to point O. Only mass we have here is the particle mass. Here is this vector, because here is the coordinate system L sine theta plus x, because point O is moving as x. Clear, guys? In I direction unit vector. And what is in the y direction? You tell me. Look at the figure. What's in the y direction? Huh? Guys? What's in the y direction? What's the displacement in y direction? Guys, can you hear me? Yeah, plus or minus in J. Plus or minus. Here is your coordinate system. 0, x, y. Y is upward. Here is, yes, plus, plus, minus, minus, because this is below the datum origin, minus. So the velocity by time derivative with respect to time, velocity of mass center with respect to point O. Now this is high school, not even university. L theta dot cosine theta plus x dot in I, and here plus L theta dot sine theta in J. Because cosine derivative is minus, 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 and plus. Again, time derivative from this, acceleration of the mass center with respect to point O is L first term, theta double dot cosine theta, plus second term in first term, minus theta dot square, sine theta, plus x double dot in I, plus L first and second theta double dot sine theta, plus again theta dot square cosine theta in J. Obviously, for God's sake, this is AX, acceleration X. Here we go. This is AY. Now let's go back to dynamic course. That's why always I say that the control is conclusion of whatever you passed in undergraduate mechanical engineering courses. Because you're gonna get help from statics, dynamics, vibration, I don't know, modeling of physical system, and now you're on a stage that you can control the system, states, and transient behavior, and steady state behavior. So, sum of the force in x direction, I'm writing. Look at here, not magic. There's no Vegas, no gambling. Which force is in the x direction? Show me. Which force only we have here? Fx, that's right. Minus or plus in x direction? Yes, because this is the looking to the left. That's right. Minus Fx equals to max. We got it here. L theta double dot cosine theta minus theta dot square sine theta plus x double dot. Here we go. Equation number 1. Sum of the forces in y direction. No magic. What forces are in the y direction? What are the forces in the y direction? Yeah, Fy plus or minus, and mg minus, because looking down, respect to the coordinate system, minus mg is m L theta double dot sine theta plus theta dot square cosine theta into. Now let's go back to, so everything is good, but the important thing is that, oh my god, we don't have fx and fy. So you know what? I'm going to calculate fx gonna be, look at here, obviously, fx gonna be minus m L theta double dot cosine theta. Don't do that. Let me rewrite it here because I want to save space. So fx, I'm just multiplying the both sides by minus, that's right. So this is going to be fx. Fx is going to be minus m this. And fy, I'm going to move the mg to the other side. Simple like that. Everyone agree? Plus mg. Why? Because now, based on the moment equation learned in dynamic course, you can say some of the moments now, because point O is moving around the mass center, around here, is I around the mass center theta double dot. Okay? Based on what I said here in the green writing, is only valid around fixed point or mass center. What is mass moment of inertia around the particle? This is particle, means has no dimension from dynamic course, only has mass. Particle means has no dimension and only has mass. What's the mass moment of inertia around the mass center? For reminding you from dynamic course and the vibration course, I, mass moment of inertia, is r square dm, distance. Particle has no dimension. So this is how much? Has no dimension, has no length, has no width, has no thickness. So what is the r here around the mass center? Huh? 0. There we go. So this side is 0. Bingo. This side is 0. mg never generates any moment because passing through that point from statics and dynamics. So the only, let me do this because I want to write it down here. So the only forces acting around point mass center. Ooh, what happened? Sorry guys. Is fx and fy. Okay, so let me do that. I'm gonna apply. We know from the statics and dynamics, moments is force in the normal distance. Fx, normal distance to the mass center, is L cosine theta, for God's sake. L cosine theta. L cosine theta. So what's the sign of that? Positive or negative? I taught you a million times in control, in vibration and dynamics course. Positive or negative? If you don't know, please learn in this class. Okay? Positive or negative? Okay. So you see that the angle is increasing, right? You want to increase that. If you fix the mass center by your point in the plane, okay, and if you apply fx, gonna increase the angle or decrease the angle? You fix the mass center by your this point by your finger and apply the fx, gonna increase the angle or decrease the angle? This is from kindergarten. Just experiment. it's gonna pull it this way. That's right, this way, right? So the angle gonna increase. Increase means helping. Helping means plus. Simple like that. Forget about the right hand rule. When I help you means I'm positive. When I resist you means I'm negative. As a society, right? Understand what I have done? Just fix this, apply the force. It's increasing the angle. Now about Fy. Fy in the normal distance. This is normal distance. L sine theta. Do the same and let me know the sign. Let me know the sign. Fix mass center, apply Fy. It's increasing the angle or decreasing the angle? Yes, so means negative. Bingo. Equation number 3. So I'm writing here. See, I'm writing here. Fx L cosine theta minus Fy L sine theta was 0 from moment equation. So what I'm going to do, for God's sake, let me separate this. Let me write this here because I want to work with this Fx L cosine theta minus Fy L sine theta is 0. Okay. Let me double check that. Yeah. So by having this in front of your eyes, you have to multiply equation number 1, both sides. You have to multiply by L cosine theta, and you have to multiply the both sides of the second equation by minus L sine theta, then add together and do the result. Let us do that together. So left hand side, Fx L cosine theta minus Fy L sine theta equals to, because we are adding. How much is this, guys, for God's sake? How much is that? How much is that? 0. Bye bye. Fx and Fy. Now let's do this. Minus, so I'm factoring out. M factoring out. You have here minus L. Let me do like this. L, because they are sharing theta double dot. That's right, and L theta double dot. Now minus here cosine square. Cosine square of theta, and minus sine, because minus comes here, factoring out, sine square. This is high school. Now plus minus plus theta dot sine cosine minus theta dot square sine cosine means bye bye after adding together. And the last term from the first line is minus M L x double dot cosine theta. And from the second line remaining is M is out. It's already factored, guys. Let me see. And from the second line is only this minus GL sine theta. Bingo. But from high school, you learned that sine square plus cosine square is how much? 1. So, and I say bye bye to M because here is 0. Here is 0. So you get this. And I'm saying bye bye to all of the negative, multiply the both sides. So you get L theta double dot plus GL. Oh, you have L square here, you guys see? I missed it. L in L. Okay, this is L squared. Good, I catch this. L squared theta double dot theta double dot plus GL sine theta, and I move this to other side, minus LX double dot cosine theta. And what I'm going to do, I'm going to divide the both sides by L squared. Can I go to next page? Everybody? So you're going to have theta double dot plus G over L sine of theta is minus acceleration of your hip joint divided by length of your leg, simplified version of your leg, cosine theta. Here we go. This is differential equation of the moving pendulum as a robot that is moving on the rover, as a model of your car. And obviously it is linear differential equation or non-linear differential equation. You tell me. You had to know this from differential equation course. Is it linear or non-linear differential equation? Huh? Guys? What's a linear function from high school? Yx. Can you help me to plot a linear function? Is this linear function? Y is equal to x. Yeah. What about this? Is it a linear function? Huh? Yes, sine of x, that's right. What about this? This is what from high school? Cosine of x. So cosine of x and sine of x are not linear, they are non-linear. So now you let me know, this differential equation is linear or non-linear? Non-linear. Non-linear differential equation. So if you want to control this moving pendulum, what do I mean by controlling? You have to understand the basic concept in the courses you pass. If you do not understand the basic concept, and if you are god of mathematics, has zero value. When I say that, I want to say when your hip moves, I want that you keep your leg at angle of 45 degrees. Here. So what you're going to do for that, for God's sake, guys, you're going to apply a torque here. That's right. Torque to your hip angle. So that happens, that you keep your leg at 45 degrees. This torque that you're applying and is being applied by your leg, I'm sorry, by your brain, by your nerves, the name of is controller. I'm serious. So you see in your body, your brain sends signal through nerves to different joints, makes what you want. You want to run, you want to dance, you want to keep your hand angle when you practicing in the gym, right? When you lift the weight and you want to keep it to the 90 degree, that's a controller issued by your brain. So designing the tau, the torque that keeps the angle of your leg, or 1 degree of freedom robot on the Mars at 45 degree, that's the control. That's the control problem. Understand, everybody? Yes? Okay. So let's go back to this before going to linearization. Always in differential equation, I hope that they taught you when you're passing the differential equation course. The left-hand side always shows internal dynamics of a system. What do I mean by internal dynamics? Means there is no external torques, control torques, external force, control force, and I want to see how the system behaves by itself. This is internal dynamics. If the system is stable by itself, this is internal dynamics. Understand? And the right-hand side, I hope they taught in differential equation course, always is external dynamics. Means I'm gonna, in the right-hand side, I'm gonna always apply torque, control signal, force, okay? To make the system behave as you would love to behave. See what I'm saying, everybody? The differential equation is not a bunch of time derivatives, has meanings. Meaning is the left-hand side is system by itself, how it behaves dynamically. Right-hand side, these are the forces, torques, control signal I'm applying to the system to move it to the target that I want it. Let me give you simple, stupid before going ahead because I have a lot to do here. I'm not done. This is your car, right? When you push the gas pedal, there is an engine force that, like this, F, goes to the wheels and goes here. So you apply Newton's second law, you're gonna get this F. This F is the amount of pressure you are applying to the gas pedal to speed up your car. So when you pressure the gas pedal or push the gas pedal, you are applying the controller. Here we go. And this is your car weight, this is your car acceleration. So the right hand side is you as controller, left hand side is the dynamics of the your car. Understand, everybody? Yes? Huh? Clear, everybody? Good. Being said, now I want to look at everything as a block diagram, because I told you I want to define it. In block diagram, guys, the system itself, this is system itself, without any controller. We name it as plant in control. Plant. Inside the plant, in time domain and later in the frequency domain, it's gonna be differential equation here. Like as theta double dot, just accept from now from you, okay? G over L sine theta. This is non-linear, but we're gonna make it linear, okay? This is concept of the control and block diagram. Okay? Now I told you guys, if you want to keep the angle to 45 degrees, you're gonna have what? A torque here. Okay, for example. So you're gonna see you have a torque. I'm gonna just apply for now. Okay, I'm gonna extend later. Is tau. Okay, tau plus tau, because this is your control signal that you're gonna design in this course. So inside you're gonna have a tau. Tau coming from where? From this block. controller. We show with C. I'm gonna show eventually. C. Okay, C. And the plants we're gonna show with G, capital G. This is convention. Okay, I'm applying a torque from the controller, goes inside the dynamics, internal dynamics of the plant. So when it does, you're gonna see the effect of that as a real output. Theta real of your real. This R is real. Real angle of your Lego robot. You're gonna tell me, Payman, you are missing some point. So what the hell is this? I want that you find it out, guys. What is that? Think about this physically. What is that? Guys, listen to me very carefully. Suppose that you're in front of me. Okay? Suppose you're in front of me. Stationary. I start to push you and pull you periodically. What's gonna happen to you? You're gonna shake, that's right? Yes? You're gonna oscillate, right? Yes, everybody? Okay. So what's the English word for that? You're gonna say, Payman, you are what doing me? You are disturbing me. So the technical word in the control class is disturbance. Disturbance. This is technical word here I'm gonna add here. Disturbance. You're disturbing the system. So this that I applied here as a hip motion is X. Okay, X double dot acceleration. You're disturbing the dynamics of the system here. Okay, so here I'm gonna show with the block as D, and I'm gonna show in the MATLAB Simulink. In Simulink, I'm gonna exactly show this eventually, how to make block diagram in the Simulink and make a simulation and this kind of thing. So you are disturbing. So you see that, guys, there's no magic. I'm just following this differential equation. The controller is being subtracted from disturbance. So you have to have a sum, and you have in the Simulink like this sum operator, it says. Here is plus, inside here is negative, is negative. So tau comes here from the controller, and the disturbance is being subtracted from that. Here we go. And the result goes to the robot, moving robot or moving pendulum. Are you following me? Yes? Yes, everybody? Just like as playing with the blocks, like as in a high school level. Okay? So now I'm making the block diagram in very, very lay language for you. Okay? Okay, good. But I told you that I want to keep the angle of your leg or this robot moving on the Mars at 45 degree, pi over 4. So when I say I want to, as a control engineer, means desirable response. This is technical term. I desire to have it, but this is the desirable response. So this theta D stands for desirable response. So this theta d is here. Okay, this I want to keep that. How much is that? Pi over 4. I'm going to show it. You have another operator here, sum operator, plus minus this time. Bear with me. Okay. Guys, suppose that you never passed the control class and you are in the high school right now. Think logically. When I apply the torque, we're going to have some real angles here. How do I have to compare the real angle with the desirable angle? I have to compare them, that's right? Yes? Yes or no? Yeah, exactly. So I'm gonna compare the real angle output. This is output, we name it. Output, as I promised you. This is output. Where is that? Bingo. With the input or reference signal. Another name of this is input. This is input. I'm comparing those. Look at here. Theta d plus minus, this is minus, theta r. I'm just showing here. So this signal is the comparison of those. Theta d, desirable that I want, and the real that is happening right now. So the name of this is error signal. Error signal. This signal goes to the controller, guys, as I promised you. Error signal. So in this course and after graduation, the company, they're gonna pay you 100K, 200K, whatever they're gonna pay, that you design a controller that gets the instantaneous error signal, issue a control command that finally makes the error signal to how much? To how much? I told you? 0. Now, when you see there is a path here, is forward, forward, forward. This is feed forward path, as I promised you. Feed forward path. You're looking forward. But when you compare the real output with desirable input, you are getting feed back. Here we go. Feedback. Understand, everyone? Yes? So feed forward is this path. Feedback is this path. You got it? Yes? Everybody? Good. I'm not done. Suppose there is no controller. Okay? And there is no feedback. So I mean that, look at here, I'm cutting the system from here. Here we go. Understand? Or let me tell you like this, not that. There is no controller. Look at here, guys. There is no controller. Only you have disturbance coming inside the moving pendulum, and it has a real out. I'm cutting from here, and this is a real output. So, do you have any control on the system to push it to the angle you want? Do you have any control on the system? No. So when you don't have, there is no feedback line. So we say, as I promised you, open the loop block diagram. Means there is no output to be compared to feedback with the input. It is open loop. Whatever you apply, you're going to see the result. That's it. There is no control. Clear? While you design controller, here we go. You design controller, you're gonna make it what? You tell me. What is opposite of the open? What is the opposite of the open? Huh? Close. You close the loop block diagram as I promised you. Close the loop block diagram. Now you have control on the system. Yes or no? Huh? I'm not done yet. When there is a real output, how you gonna compare with the input? How you measure the output physically, not mathematically? You tell me. How you sense the temperature of a room that is 75 degree, 80? How you measure it? Sensors. So in the feedback, you have the block that we name it H, sensor. Use real output to be sensed through sensor. Then I'm going to omit this. I'm going to teach you mathematically why. There is a sensor that measures this to be compared or subtracted from the input and gives you error signal. Based on this error signal, we're going to design controller. Comes here, being summed with the disturbance, goes to the system, and this loop continues until error signal goes to 0. And can you believe that every day you are using your car cruise system, you are running this loop every day? So if I want to clear it up, let me do that for you. This is the big picture of, we name as X, generally speaking, desirable input or input of the system. This comes to error signal. This is whole picture of the course. C, controller. U, we are showing U as general control command and control. Even if you go to grad school, you're going to show with U. Suppose you have a disturbance. D, I'm going to show it in the MATLAB simulating, in the simulating part, is being summed. Say plus plus, I don't care. Plant, G, system itself. We are showing with Y, output, real output, is being measured by sensor and being subtracted from the input to issue the error signal. And this is the whole picture of a control engineer making 100, 150K per year. Crystal clear? Crystal clear? Yes? Good. So I'm not done yet with this because lots of math we have here. I have to do it in the week after this, okay? I'm not done yet with this. I just wanted to bring out of a real example that why you are taking ME 530 and which tools eventually you need in the coding and Simulink and math to design controller, lead lag controller, root locus, body plot, these kind of things. That these are the tools that I'm going to teach. Got it? Yep. And before